Alright, welcome back to Geology here. And this week we're going to take a look at Glaciers and Glaciation, Chapter 18. So glaciers are parts of two basic cycles, both the hydrologic cycle of water and the rock cycle, which we have discussed both in depth now. A glacier is a thick mass of ice that originates on land from the accumulation, compaction, and recrystallization of snow. There are various types of glaciers. There are valley, or otherwise known as alpine glaciers. These exist in the mountainous areas and flow down a valley from an accumulation center at its head at the top of the mountain. And then there are ice sheets. These exist on a larger scale than valley glaciers. Two major ice sheets on Earth are over Greenland and Antarctica. So here's the Taku Glacier near Juneau, Alaska. You can see that it also has a fan delta, an alluvial fan, the way it spreads out, and it retracts and retreats and moves forward as the seasons go along. Ice sheets are often called continental ice sheets, and ice flows out in all directions from one or more snow accumulation centers. Other types of glaciers include ice caps, outlet glaciers, Piedmont glaciers. Well, what would happen if the ice on the Earth melted? And this is a question climate scientists are dealing with right now as we look at the possibility of global warming. Well, slightly more than 2% of the world's water is tied up in glaciers. The Antarctic ice sheet, 80% of the world's ice is there. Nearly 2/3 of Earth's fresh water is there. It covers almost 1.5 times the area of the United States. And if melted, the sea level would rise 60 to 70 meters, which would inundate most coastline areas. So here we see a diagram of the United States and North America. This is what would happen if the present ice sheets, including Antarctica, would melt. You can see that the entire state of Florida would be underwater. We can see that the Mississippi Delta would back up all the way to Memphis. Houston would be inundated. New York City would be inundated. Most of the eastern seaboard would be underwater. Well, glaciers form in areas where more snow falls in winter than melts during the summer. And so here are the steps in the formation of glacial ice. Air infiltrates the snow. Snowflakes become smaller, thicker, and more spherical, and the air is forced out. Snow is recrystallized into a much denser mass of small grains called firn. And once the thickness of the ice and snow exceeds 50 meters, firn fuses into a solid mass of interlocking ice crystals, which is called glacial ice. Now let's look at the movement of glacial ice. There are two basic flows, plastic flow and basal flow, or basal slip. The plastic flow occurs within the ice, and it's under pressure, and as such the ice behaves as a plastic material. Basal slip is the entire ice mass slipping along the ground, and this is what most glaciers are thought to do when they move. Movement of a glacial ice is called flow, and we can look at the zone of fracture. This occurs in the uppermost 50 meters of the glacier. The tension causes crevasses to form in brittle ice. Average velocities vary considerably from one glacier to another of movement. Rates of up to several meters per day have been reported and recorded for glacial movement, and some glaciers exhibit extremely rapid movements called surges. Now, the zone of accumulation is the area where a glacier forms, and the elevation of the snow line can vary greatly. The zone of wastage is the area where there is a net loss of ice due to melting, or what is called calving, the breaking off of large pieces of ice, icebergs where the glacier has reached the sea. The balance or lack of balance between accumulation and loss is referred to the glacial budget. If the accumulation exceeds the loss, called ablation, the glacial front advances. If ablation increases and or accumulation decreases, the ice front will retreat. So here's the glacial budget. We can see the crevasses there and the snow line, and the zone of accumulation where more snow falls each winter than melts each summer, and the zone of wastage on the bottom, where the snow from the previous winter melts along some of the glacial ice. Now let's look at erosion. Glaciers are capable of great erosion activity and sediment transport, and they can erode the land primarily in two ways. One is called plucking, where they lift the rocks. Another is called abrasion, where rocks within the ice acting like sandpaper to smooth and polish the surface below. Glacial abrasion produces rock flowers, which is pulverized rock, and glacial striations, which is grooves in the bedrock. Major landforms can also be created by glacial erosion. Erosional features in valleys include glacial troughs, truncated spurs, and hanging valleys. So here are some scratches and grooves in some bedrock produced by glacial erosion or abrasion. Some of the landforms created by glacial erosion in valleys can include paternoster lakes, cirques, tarns, fjords, arties, and horns. So here's a diagram of this. This is in your book. I won't go over it here. You can look in your book to see this diagram, and you can see where the different formations form. Here's a U-shaped glacial trough in Norway, and the famous Matterhorn in the Swiss Alps. Glacial drift refers to all sediments of glacial origin, and types of drift include till and stratified drift. Till is the material that is deposited directly by the ice, and the stratified drift sediments laid down by glacial meltwater. Glacial till is typically unstratified and unsorted. Deposits made by the glacial deposits of landforms can include moraines, which is a layer or ridge of till. Moraines produced by alpine glaciers include a lateral and medial moraine. There is an end moraine, which is a terminal or recessional moraine, and a ground moraine. These terms are in your book and defined. Here are some extent of medial moraines in Alaska. Here are some glacial deposital features in your book. This is also in your book. Some other landforms made by till include drumlins, which are smooth, elongated, parallel hills. The steep sides face the direction from which the ice advanced. They can occur in clusters called drumlin fields, and the formation is not well fully understood. So here are some drumlin fields near Palmyra, New York. Landforms can also be made of stratified drift. These include outwash plains with ice sheets and valley trains, which is when they are in the valley. A broad ramp-like surface composed of stratified drift deposited by meltwater leaving a glacier. They are located adjacent to the downstream edge of most end moraines and are often pockmarked with depressions called kettles. Ice contact deposits can be made by meltwater flowing over, within, and at the base of motionless ice, and these features include kames, kame terraces, and eskers. Now let's look at the glaciers of the past. There are indirect effects of Ice Age glaciers, talking 10,000 years ago. Forces migration of animals and plants, changes in stream courses, rebounding upward of the crust and former centers of ice accumulation, worldwide changes in sea levels, climatic changes, and pluvial lakes. The crustal rebound following the removal of glacier ice. You can see that the rebound of the surface crust, the rock bedrock, and sea level changes over the past 20,000 years. We can see here that really about 18,000 years ago, we were standing about 100 meters less than what we are now, present day. The present day sea level really has been constant since about 6,000 years ago. And during that ice age, 10, 20,000 years ago, the maximum extent of glaciation came pretty far down towards about the Iowa-Missouri border. There's a stark contrast if you drive from the Ozarks and near Springfield, Missouri, up through Iowa. You can really see in the landscape in the fields the vast difference there is in the glaciation. Well, any successful theory must account for what causes the onset of glacial conditions and what caused the alteration of glacial and interglacial stages that have been documented in the past. So here's the maximum extent of ice sheets in the northern hemisphere. We can see that they do go pretty far deep into Russia, Iceland, which is really green, the Alps, and deep into the United States. So some other possible causes of glaciation include plate tectonics, where the continents were arranged differently in the past, and changes in oceanic circulation. Also, variations in Earth's orbit. We do believe that the Earth's orbit does change over very long periods of time, on time frames of 100,000 years or more. And this is called the Milankovitch hypothesis. Well, let's look at the Milankovitch hypothesis. We believe in this theory that the shape or the eccentricity, how elliptical the orbit is of the Earth, changes. The angle of Earth's axis, what we call obliquity, changes between 22 and 24 degrees, where we are currently at 23.5 degrees. We know the Earth's axis wobbles, and this is called precession, and this takes 23,000 years to occur. Changes in climate over the past several 100,000 years are closely associated with variations in the geometry of Earth's orbit, and other factors are probably also involved. That's the end of chapter 18. We're almost done. Hang in there, and we'll see you on the discussion boards.